Okay, so this is the Quantitative Methods Network, and my name is Mike Zephyr. I'm an associate professor at the University of Melbourne in the Faculty of Business and Economics. And today our speaker is Simon Dennis, and he's going to be speaking to us about privacy-sensitive data analysis and how to address the failures of existing statistical programming languages in relation to privacy. Professor Dennis is the director of the Complex Human Data Hub here at the University of Melbourne in the School of Psychological Sciences. And his training is in, his PhD is in computer science, and his research utilizes large-scale real-world data, experimental paradigms, and computational modeling techniques to investigate the cognitive architecture underlying memory and language, with a lot of work on language. If you look at his Google Scholar page, much of his research uses experience sampling methods to study psychological processes, and he's done a lot of work through his company, Unforgettable Research Services, and his app, Unforgettable Me. You're the CEO of that, aren't you, Simon?
I am indeed, yeah.
Pretty fancy. So, Simon, why don't we turn it over to you, and you can feel free to share your screen, and that should take over the whole thing.
Okay, cool. So I will do that.
Okay, cool. And I'll just cut my video off here so you can have the whole thing.
Okay. So can everyone see that? Is that good?
I cannot. Can anyone else?
No?
No, I can't see it.
Let me see advanced sharing options.
Okay.
There you go.
Sorry, there was an extra button press to go. Okay, how's that?
That's great.
That's great. Okay, thanks, Mike. And yeah, so as Mike said, I'm Director of the Complex Human Data Hub in the Melbourne School of Psychological Sciences, and also CEO of Unforgettable Research Services. So what I wanted to talk to you about today is the use of big data and some of the perils that embodies. So certainly in psychology, and I think in a lot of health sciences and other behavioural sciences, there's the promise of big data is just enormous. In my view, big data may well be when psychological science really comes of age, because to tell you the truth, if you're a critic, you might say that the degree to which psychological science has had real impact has been somewhat limited given the significance of the topic that we study. And so I think one of the big reasons for that is that the scale of the data that we've been operating with is really not sufficient to the kinds of questions that we would most like to ask. And I think we can really take that to a new level now with the new data collection mechanisms that we have. However, big data has two sides, right? It's one bear, but two sides. So there's the positive of what we might be able to achieve in terms of behaviour change, in terms of people's mental health and so forth. But on the flip side, we have this very significant issue about people's privacy. So unfortunately, it tends to be the case that the most useful data is also the most sensitive data. And in my view, we're going to need to think laterally and quite deeply about our fundamental relationship to data in order to appropriately address the privacy concerns that this kind of data creates. And so to give you, just one example of this, and I'm assuming many of you would be familiar with the Cambridge Analytica scandal. So 87 million Facebook profiles were taken. That's an estimate at least, and potentially used to influence the US presidential election. We don't really know whether they did influence the US presidential election, but certainly that was an attempt was made to do that. So one of the major protagonists in this story was Alexander Kogan, who's a social psychologist, and but in every other way appeared like a legitimate scientist. And he studies personality. And what he did was, he's a research associate at Cambridge University, and he created this app called This Is Your Digital Life. And it tested the big 5 personality traits. Now, what happened, there was about 270,000 people who used the app, but the app not only collected their data, but it collected data from all of the people that they were friends with. And that's how it came to be, to expand as rapidly as it did. Now, the thing that's important to realize, there's a couple of really salient points about this case, I think. So one of them is that the Kogan was, he was affiliated with Cambridge. He was, not a super well known, but he was a known social psychologist. And he wasn't just hacking in. So it was known to Facebook that he was doing this. But what the story kind of illustrates one of the fundamental aspects of data, and that's that once you get access to the raw data, it can be distributed, right? There's nothing stopping people from copying it. And in fact, that's exactly what happened in this case. And so originally, it went from Facebook to Kogan. Kogan had a company. The data then skipped to another company called SDL Elections, and then ultimately to Cambridge Analytica. And so that just kind of illustrates, that once the genie's out of the bottle, there's not a lot you can do about it. There have been, in the UK, there have been efforts to get all of that data deleted and so forth, but how would you know? It's very difficult for us to really know whether that data is still available or not. And so the first lesson there, I think, is that we can't just rely, that once data gets out, there really is no way to put it back, and we can't just rely on the good graces of the people that are analysing the data in all cases. Now, I'm not saying that there's a lot of people like Kogan, but as you increase the number of people who have access to the data, you simultaneously increase the risk, right? And to this day, Kogan contests that he did nothing wrong, right? So as far as he's concerned, this was all perfectly legitimate. So, and I guess that is underlined by this kind of statement. This comes from Sandy Parakailis, who was worked for Facebook at the time that this was all happening. And he's explaining here to 60 Minutes, that how you would get access to the data from one person who was using the app. They would be asked about that, but then when they were asked about that, they were also asked if it was okay to grab all of their friends' data as well. And if they said that yes to that, they just got the whole lot. But so that's how it got so big. And the key point is there was no hack, right? So certainly security remains an issue, and there are lots of breaches of security. But in this case, that wasn't what happened, and we need to be aware of these kind of insider possibilities. Now, I would argue that current data analysis languages don't preserve privacy. So essentially, they make no effort whatsoever. The assumption is typically that if you are looking at if you have access to the data, if you're given access to the data, you should have the right to see everything. Okay, and so you can imagine, you've got some set of emails. It's easy enough to go through, find somebody's email, and potentially find information that they would not necessarily want the entire world to know. Furthermore, I think it's actually quite challenging to retrofit existing languages. The demands of inserting a kind of computational privacy mechanisms in such a way that they cannot be circumvented are really quite difficult. So, particularly languages like R and Python, for instance, were never designed to be able to stop people getting to that underlying data. And in fact, they're much more permissive than other more general procedural languages often are. And it's really going to be quite difficult for us to do anything about that. So what I want to talk to you about today is our kind of solution to that problem. And it's a new language called Private. And it has a number of characteristics which are designed to aid in the ability to make sure people's data is protected. So one of the things that you have to get right to begin with in terms of protecting people's data is you need this very tight coupling between the data and the analysis, right? So as I was saying before, as soon as the data has been copied anywhere, you know, your protections are basically worthless, right? So, so the only real way I can see to protect that at the moment is by having a very strong coupling between the data and the analysis, i.e. if you want to do analysis on a data set, you go to the machine where the data set resides. You don't transfer the data to the machine, to your machine to do the analysis. And so in Private, that's what we do. So when you want to do a private analysis, you log into the system and you operate within a shell that's in that system. What Private does is it tests any result to determine whether it should be released to the coder. So you write your program, it executes, and it has a series of tests. So it knows what data is private in the first instance, and it looks to see, is this result either directly, deterministically related to private data, or if it's probabilistically related to private data, is that probabilistic result too sensitive to the inclusion of any given individual's data? And so all of these, I'll expand on those tests later, but all of these mechanisms are kind of built into the language. So you, everything is tested before the coder gets to see it. It's both a probabilistic and deterministic language. So one of the key things to keep in mind is that if you have an arbitrary deterministic language sitting on the top of data, even if I somehow protect you, stop you from accessing the raw data itself, if there are deterministic calculations that you can do on top of that raw data, you can then reverse engineer people's private data. So it's anything where there's a direct flow of information from a private source to a result through deterministic calculations is a risk, is a potential violation. So that means that in order to get information out, you need to be operating with probabilistic variables. And so what Private does is it takes this opportunity to say, okay, well, let's work in this Bayesian framework where we're constantly in the process of generating samples, and what we're going to be doing is testing those probabilistic samples that we generate in order to see how sensitive they are. So the language itself is based on Python and also Bugs, JAGS, Stan. So it has those same kind of primitives in it. It's a declarative language. So most of the languages that most people are familiar with, like Python and R, are procedural languages. So so there is a state that the execution of the program is in at any given stage. You execute a command, and then that updates the state. In declarative languages, and if you've used Bugs or JAGS, then they are examples of declarative languages, there is no state. So for a given declarative program, each variable has one and only one value, and the program's job is just to calculate what those values are. And that's really useful because when you're starting to reason about the privacy of different variables, you don't have to worry about state. So all you have to do is determine that, given a program, you just determine the privacy of that variable, and you don't have to say, you don't have to worry about the fact that that privacy status might change as a function of state. Private, unlike other languages like JAGS in particular, where you have a declarative definition of some kind of probabilistic program, and you basically define it and then you execute it. In private, you can actually do incremental definition as well. So that makes it kind of more like a Python or R, where you can be constantly updating the program, you know, and trying out different things, and seeing what the results of those changes are in an incremental fashion. And that makes it easier to learn and makes it easier to work with when you have very large jobs that are operating over long time periods and so forth. Private takes the opportunity to automatically parallelize. So another important characteristic of declarative languages is that they tend to be a lot easier to automatically parallelize, because again, state is a blocker to parallelization, and so we've taken the opportunity to parallelize computation. So private operates over a cluster, and you don't need to worry about that. That's all handled underneath the hood, but it is being distributed across many cores and across many machines. And just to give you an idea, we use a bunch of different technologies. So we use PyMC3 as our basic underlying Bayesian MCMC sampling software. We use Redis, we use DAS for parallelization, Arpeggio for parsing, S3 for a lot of our storage, and then Seaborn for some of the plotting and so forth. And private is open source. Okay, so that gives you a kind of overview of how private, the kind of design characteristics of private. So I'm just going to kind of go through in some more detail and do some examples. Just to reiterate one of the points I made before, there's no setup or installation with private. You just log in, because in order to preserve privacy, you need to have this very strong coupling between the data and the analysis method. And so you log in, and the data simply exists in the current environment as soon as you log in. Okay. So you don't have to load it, you don't have to import it or anything like that, because all of that introduced as potential exploits. Now, so for those of you who've used something like JAGS or STEM, the typical way of doing that these days, at least, is to write your program in either R or Python or MatLab, and in the first instance, and do all of your data wrangling there to get things into the appropriate format. And then you execute a call to JAGS or STEM, and you have another program written in JAGS, say, and then you pass all of the data from R or Python into JAGS. It does its computation, then all of the data gets passed back to R or Python, so that you can do calculations, any kind of post-processing that you want to do on that data. Now, because we can't be having data flowing backwards and forwards like this between different programs, etc., what private does is it embeds everything within the language itself. So, so to give you an idea, we might have a calculation. So here, what I'm doing is generating 100 Bernoulli samples with a rate of 0.3, and that's going into a variable called L. SV here stands for show variables, and so show variables shows me the definition of this variable, and then a kind of truncated representation of the value of that variable. So, and then if I want to see the whole thing, I can type L here, and this shows me all of the samples. So this generated a whole set of, or 100 samples, all of which are ones and zeros based on this rate parameter. Now, here I've used the equals. So even though this is obviously creating a random sample from a Bernoulli, that is still a deterministic calculation, because the all of our seeds are fixed seeds, and they will always generate the same result. So I'm not when I say a deterministic calculation, I don't mean there's no randomness in it. I mean it's not a calculation that's going to be coming out of a sampler. So here what we've got is L is equal to that, and we can use that as a way of kind of generating dummy data, if you like. Now, where this will differ more from something like Python, for instance, is that we also have the ability to define certain probabilistic definitions of variables. So here, what we've done is we've said L is distributed as a Bernoulli with a certain rate. So now what that is doing is setting up our definition of our likelihood for L. And so we're saying it's a Bernoulli distribution with a rate R. Now, in this case, we know that's exactly correct because that's how we generated the data in the first place. But this is where you would have to figure out, what model you're going to propose. And so once we've done that, we can do an SV again. We see L here. We have two definitions now, one deterministic, one probabilistic, and these are going to be the same because L only has one value, in this case, a vector of 1s and 0s. At this point, though, right, we don't have enough for us to be able to actually calculate the rate, right? Because in a Bayesian model, we need not only the likelihood, but we also need the prior. And so in order to do that, we define the rate, the R parameter here. So we say that's distributed as a uniform between 0 and 1. And then everything starts, right? So private is going through analyzing the variable dependency tree of the program that you're calculating. And as soon as it has all of the components that are required to actually start sampling, it does. Okay, so there's no line where you say now start the sampler. It just says, okay, well, I've got everything I need now, and so off I go. I can start computing the result. So I've done an SV here. Obviously for this sampling, there's not very much to do, so it won't take too long. But you can imagine as the programs become more complicated, the sampling may take a long time. And so what's going to happen is it'll be in this computing state. So notice it doesn't block. So you don't finish the program and then have to wait for it to finish. It immediately comes back, you've defined your program, but then once you look at the variables, you'll see it's in this computing state. Okay. And because it doesn't block, you can keep going, right? So it can be going away, doing whatever long and involved computation might be required, and you can continue programming, right? So let's say we figure, well, yeah, we've got that running now. I know I'm going to want the mean of that and the standard deviation of those samples when it comes back, so I can go ahead and define those. Okay, and this is what I mean by incremental, right? So this is different from what you typically see in the interaction between, say, JAGS and R or JAGS and Python. So the definitions can be added incrementally. If there's a change that actually would change the model, then what will happen is it'll then restart the calculation. So if we change the likelihood, for instance, then that's a change to the model, right? And so now we have to go through and recalculate redo the sampling. So what private does is it always aims to keep the variable's values consistent with whatever the definition of the program is that you've currently included. Okay, so we're done. We finished the computation of those samples. The sample is finished. And you'll notice, so down here you can see we've got R as a uniform. Here's a set of samples that have been generated from that uniform. And now mean R and standard R or STDR have been automatically calculated. So private's looking, it realizes when the sampler finishes, it looks for all of the dependencies all the variables that are dependent upon that result, and it automatically does those calculations to make sure that those results are up to date. So as I mentioned, it's declarative, so the variables are all updated automatically. Okay, so let's say I went through it, I changed my data now. Okay, so instead of a Bernoulli with a rate of 0.3, I've changed this to a Bernoulli with a rate of 0.9. So all I do is add this in, that line in, and then it knows, oh, okay, that means I'm going to have to go through and resample. And so I've just shown the end of the computation here, that it's gone through, resampled, it's recalculated mean R, recalculated standard deviation R, and so forth. So unlike a procedural language where you're often in the, if you change one of the assumptions, say one of the variables, one of the parameters, the fixed parameters, for instance, you would then be responsible for going through and making sure that all of the variables were updated appropriately, rerunning the pieces of code that you needed in order to make sure that the whole program was properly up to date. So with private, you don't need to do that. It's the language itself is making sure that you're up to date. So, and I would argue, my suspicion is that there are a lot of errors that we see which are a consequence of the procedural nature of the languages we use. And I think that private will be able to minimize those kinds of errors. Things like plots are also declarative. So if I say R plot here is equal to a distribution plot of R, then I get a plot that looks like this. And so this is the initial look at this point in time, what that'll look like. But then if I go through and change this now to Bernoulli 0.5 with 100 samples, it'll go through and change the samples. It'll go through, recalculate the means and standard deviations, but it also goes through and automatically updates the plot. Okay, so again, there's never a situation where you can, at least out of the private language, where you can get the plot, the wrong plot, because it will automatically update that, even if it doesn't rely on you to remember to rerun the plotting code. There's the sampler, so it's a uses the PyMC3 sampler, as I mentioned. So PyMC3 sampler is a kind of hybrid sampler. So by default, it uses Hamiltonian Markov chain Monte Carlo methods, but it'll switch between different methods based on the nature of the program that you give it. And you can control the sampler just by changing some variables. So number of samples, numbers of chains, numbers of tuning samples, and you alter the number of samples, for instance, and it'll go through and realize that requires a update of the chain, and it'll go through and recalculate based on the current program. And there are some standard kinds of convergence metrics. Well, one main one actually, which is R hat, Gellman and Rubin's R hat statistic. So that's automatically calculated. So you just need to look that up for the variable you're interested in by looking at R hat after the sampler is finished. And there are a few different variables for looking at model selection as well. So there's a WAIC in there. Again, you just look that up after the sampler finishes, effective sample size, leave one out, cross validation. So those give you the capacity to look at how well how different models compare to each other and so forth. I mentioned that it does parallelism automatically. So if I say want to generate two sets of Gumbel samples here, so it's got a lot of samples because otherwise it finishes too quickly. But let's say I define T equals to this one, T2 equals to this one. These don't depend on each other. And it knows that because it has the entire dependency tree of the program. And so it realizes that these two things can be done in parallel. So it's got two jobs, it sent these off to different machines automatically. So, so it kind of takes all of that parallelization effort away. Bunch of built-ins that it has. Basically, these are inherited from Python and from PyMC3. and then a bunch of probabilistic built-ins that you can use to build up your model. Okay, what am I up to? So that's all great. There's lots of advantages there, but the language is called private, and that is its primary purpose, and that's to make sure that people don't get access to information that they shouldn't. So, and it's called private because if you type in a private variable, it doesn't come back with what the value of that variable, it comes back with private. So in a private shell, there's always a variable called event, and events will be private, and that's where all of the data is. Okay, so you can't just look at it. Okay, so just for illustrative purposes, so that so you can kind of understand what's going on under the hood. In our kind of demo projects, we also provide a variable called demo event. And so this is all fake data now that you're looking at. And demo events is exactly like events, except that it is not private. And so therefore you're allowed to look at it. So this, what you're looking at here is data that comes out of the unforgettable system. So we have an app that collects a GPS, accelerometry, some kind of obfuscated audio components, and battery levels, and a few other things. And so those are then, it does that in our segments. So our participants, users go out into the world with their phones, and it's collecting all of this data all the time. And then that comes back, and you can access that in the private shell by looking at event, one of the events from, say, demo events or events. And so here, this is just one of them. So this might be demo event 0, for instance. So you've got things like accelerometry counts. So how many blobs of data did we get, of accelerometry data did we get from in this hour period? What are some other key ones? Things like the start date time, the weather, the battery level, the address, things. These down here, we've got a bunch of tags that have been created by running machine learning classifiers over our audio data, and so all of these just automatically get inserted in here. And so, so what you can do is access all of this data from within the private shell. Okay, so let's run a little bit of an example just to kind of solidify how this works. So, and what I'm going to do in the first instance is I'm going to run through the example using the variable demo event. Okay, so remember, demo events is a public variable, and so this is going to allow us to actually see all of the results. What I'm going to then do is I'm going to go through doing this with events, and so that'll allow you to see what it would look like in the normal case where you don't get to see all of the underlying data. So I'm going to try a simple example here. So we've got rain is going to be a big variable which contains the status, like whether for each of our events from our app, whether it rains during that hour period. So here we've got, this is a list comprehension in the format of Python. So we've got demo events here. We're going to take each event within demo event. We're going to say, we're going to choose the weather field from that event and say, is it equal to rain? So this is going to be a whole bunch of trues and falses depending on whether the weather is equal to rain for that particular event. Now, the other thing I have to do is I have to include this test here to make sure that this particular event has a weather field. Okay, and so that's because these events could be any kinds of things. They could be emails, they could be results from experiments, they could be button presses, they could be kind of micro surveys that have been generated from ecological momentary assessment and so forth. So there's lots of different kinds of events that can exist within my data set, and not all of them have weather. And so you just have to select out for the one that has weather. So we do that, that will then start executing, and then when that finishes executing, it comes back with a series of trues and falses. Now I'm going to define the same program that I did before. So I've got range. I'm going to say that's distributed as a Bernoulli with a rate R, and I'm going to define the prior of that rate as a uniform from 0 to 1. And so just as we did before, that goes off and starts computing now. And comes back, and here's a series of samples from the sampler. We calculate mean, and so this is our mean for our fake data. Now, what if, so normally that wouldn't happen, right? Normally I wouldn't be able to see the underlying data, and normally I would just have the event variable instead, okay? So what would happen, so I'd be defining range now instead in terms of the event variable, and instead of coming back and telling me, which was the list of trues and falses, it would come back telling me that's private, right? Because this is a deterministic transform from a private variable, and so therefore range must be private as well, right? Because it can be exploited to reveal private information. So now I go through, do the same thing again. Again, it's computing. There's private here. And you'll notice a lot more jobs here now than I had before. So let me just see. Yeah, okay. So, so what it's doing now is it's going through and it's saying, don't just calculate the samples for all of the data, but calculate the samples for all of the data, but then also for the data set with each individual removed from it, okay? So there are 10 individuals in this data set, I believe, and so there are 11 jobs. One is the sampler doing everything with all data in. The other 10 is the sampler running with each one is one person missing, okay? So what we end up with are 11 distributions of samples at the end. And so it goes through, it does that sampling, and then, so before it was computing, now it's gone to the privacy unknown case. And this happens when it's done the all case, so it's calculated samples with everybody in, and now it can start comparing that set of samples to the set of samples for each of the, when one person is missing for each of those processes. And so down here, this is what it means when it says manifold privacy jobs. It's going through and doing that comparison of distribution. So just to kind of solidify that kind of understanding, I've taken 4 random people off the internet here. And let's suppose what we're interested in was the amount of red that they typically wear, okay? And so we've got a distribution here, and to start off with, and so this is across all of the individuals, right? And so we've got the first process goes off and it calculates the that distribution of our underlying parameter we're interested in with everybody included. And then it goes and calculates again with the first person taken out, again with the next person taken out, again with the third person taken out, and again with the fourth person taken out. And you can see in this case, right, so because Melania wears more red than the guys, when she's removed from the sample, all of a sudden the distribution shifts to the left, okay? And so, so that's the indicator, right, that this is not safe. So because it may well be that Melanie doesn't care if you know she wears red, but if it was some other type of detail she did care about, then the fact that this distribution is significantly shifted says, okay, this one is different to this one, and therefore something's being revealed about one of the people in that sample. Okay, And so therefore we would say that should not be released, and it would come back saying private, just like the other ones do. Okay. However, if that's not the case, if all of these distributions look sufficiently similar to the all one, then we say it's okay. And so that was the case in our example that we're running. And so now we've got the samples are visible, and so now you can calculate mean R on that, and you've got the result coming out there. Okay. So that's essentially how the whole thing works. So just to wrap up, so in my view, behavioural science is undergoing a revolution. So certainly in psychology, I think the ability to access big data sets, dense data sets about people making decisions about the nature of people's environments as they go about the real world is, I think, a game changer, because I think a lot of the reason that psychology hasn't had the impact that you might have expected is because we've been restricted to either experimental situations, which are too far removed from many of the real world decision-making circumstances that people are in, or we've used survey methods or something like that, where you're getting very brief snapshots of a person's attitudes or something like that. So big data, I think, is a game changer. But I think we're at a point now which is really critical, because if we don't get our analysis right, if we don't properly respect people's privacy, if we don't understand that this requires not just a change in technology, but a change in the attitude that we have towards data. If we get that wrong now, that may prevent us from being able to use that data. And we're kind of seeing that, potentially coming to pass with the tech giants, where they've obviously been the first to jump on this and realize that the importance and the value of that data. But if you don't do it the right way, people will push back, and you'll see legislation, and we don't quite know where that's going to end. But it's not a position that that people in academia want to find themselves in. We want to be on the front foot. We want to be making sure we're doing the right thing from the outset. So that means we need to be much more serious and careful about people's privacy. So as I said before, right now, the typical data analysis languages that people are operating with make no effort whatsoever to preserve privacy. And so in my view, that's just not good enough. So private is kind of our first attempt, and I would absolutely accept that it's not likely to be the last one, but it's our first attempt to say, okay, how could you rework this? How could we do this in a way that really takes the privacy seriously, and hopefully build in some other nice aspects in terms of parallelization, in terms of protection against some of the most insidious kinds of errors and so forth at the same time. So that's it from me. I'm happy to take any questions. Can't hear you, Mike.
Sorry. That was great. Thanks, Simon. Does anybody have any questions for Simon? Or rather, there are definitely going to be questions. So who would like to go first? I'm happy to, if nobody else wants to chime in. Yeah, one thing I'm wondering is, and I kept thinking about this as you were going, something like deploying and learning a new language, and no matter its benefits, and certainly in this case, given its what look like pretty substantial potential benefits, getting kind of organizations or even professional bodies on board with something like this requires, various kinds of individual, but also institutional change. So at the very end, you were referencing, which seems absolutely right, you were referencing kind of the dire need for this, and what will probably be, regulations that will at some point in the future be imposed on us and other communities if we don't take charge. And we might not like those regulations. So the ability to police ourselves gives us, arguably better terms. But how do you create that kind of change? I mean, how do you get for something like this, and what are your plans moving forward to get people interested in the language and get, I'm thinking like the ARC or NHMRC, for example, could have a little checkbox, did you use this language to analyze your data, or if you're going to share your data, can you ensure that it's going to, something like that. I don't know. What are your thoughts on that?
Yeah, so I think it does come down. So the first thing, right, is that before people are going to use it, they're going to want to be confident that it's a robust system. It really does what it's purporting to do. We still are kind of working on how do we make it more usable and so forth, and to decrease those kinds of barriers. And one of the reasons for making it open source, right, is so that some heavy duty computational privacy people can come in and try to poke holes in it and so forth, right? So I think that's kind of the first step, right? You got to be confident that it really is going to do the job. Once you're confident that that's the case, then I think it does come down to looking at various different decision-making bodies. So, and I think there are different kinds of stakeholders here, right? So you could imagine, right, that you have some kind of medical institution that carries data, and so if you could say to them, you've got a strong case, this really works, then you could say, they could make that the requirement, right? So you've got to have something like this before you get access to the data. And so then you could kind of look at various different institutions and then you're kind of in a tech diffusion kind of state, right? Where there'll be some early adopters, and then a big clump in the middle, and some sort of standouts and so forth. So the question is, so then the effort has to be around, well, who are the early adopters, right? Who are the ones that are kind of get things off the ground? Obviously, if you can get NHMRC or ARC to say these things, and it's not impossible. We've seen a lot of journals now making stipulations about replication kinds of practices and requirements for open sourcing your data and so forth. But imagine this kind of data. What are you going to do? You're not going to open source it, right? I'm certainly not sending my emails all around the world, right? So that's going to be a fundamental challenge they're going to have to deal with, and so you may see the journals saying we need to adopt something like this, or ask people to have a language like this as the way they do their analysis. The other people that we've had a little bit of interaction with is the ethics board at Melbourne, and because we have such sensitive data, ethics takes there's a lot to worry about in our kind of data with ethics, and so running through we've become close personal friends of the ethics board, because we're constantly explaining what we're trying to do with this data and why we need it, etc. But that relationship then opens up the opportunity for us to talk about this, and so before COVID, we were actually going to do a session with the people who are on the ethics board. So there's multiple ones at Melbourne, and so one of the things we were going to talk about there was privacy in general. So we've done a bunch of other privacy work about what are the kinds of key elements that influence people's decisions about whether they consider a project acceptable or not. But also we were going to talk to them about this kind of language, make sure they're aware that the technology exists, and so they know it's kind of over the horizon. It's something that perhaps in the most sensitive cases, they might start thinking about, well, you know, for those kinds of cases, maybe we really do need to do this.
Right. Yeah, that makes sense. Okay.
Any other questions?
Simon, so if I'm building a more so it looks like you've got your basic statistical Bayesian language in there.
Yep.
What facilities have I got to build more? If I want to, you know, I want to put a cognitive model inside the data,
right.
and so I'm going to. I mean, let's put aside custom samplers for a moment, but I just get the PyMC functions that I can use to build stuff. Is that kind of it?
Yeah, so at the moment that's the case. You can define your own deterministic functions, and so they just have normal Python kind of syntax and so forth, and so you can do that. We haven't implemented yet. So PyMC3 has a facility for adding in new likelihoods and things like that as well. And so we haven't actually implemented that yet, but that's the next kind of step, is to incorporate those in. But the basic functionality for doing deterministic functions, which is what the likelihoods rely on, that already exists.
Thank you.
Anybody else? We're bumping up against 3 o'clock here, but
Yep.
Happy to go for another. Oh, Andrew, you're muted.
What's the timeline on this actually appearing? I mean, is it still development, right?
Yeah, well, I mean, it's a process, I guess. I don't know if there's going to be a specific launch date, but you know, I'm teaching it in classes now, and so there will be a cohort who are familiar with how it works. Yeah, I mean, the code exists. We're actually, I guess I would say when I would be kind of more comfortable about broader adoption will probably be in the next 3 or 4 months as we go through, because we're at the point now where we're starting to you know, look at our coding standards and all that kind of stuff, so that it's kind of easier. So it's already open source, it's already on GitHub, but you know, it's not all of that tidying up hasn't been done. That's really required for you know, for other people to seriously be able to work on it. So so that's kind of all in process at the moment. So but it's you know, it's up right now. You can go and run it in Unforgettable and so forth if you're keen. And if anyone is keen, feel free to send me a line and I can set you up with the accounts and so forth, so that you can get access and play with it.
Great. 3:01. What do you think? Should we stop it there?
Yeah, it's probably
Okay.
good. Time for
Great.
coffee.
Thank you so much, Simon. That was fascinating, and obviously, you know, I mean, given concerns over privacy in a wide variety of different contexts, you know, we're going to need kind of all hands on deck, and what you're developing looks really promising. Thank you so much for taking the time to share it with us, and we'll post it to YouTube and tell the world.
Okay, excellent. Well, thank you very much for inviting me. It's fun.
Of course. Thank you so much. We'll talk soon.
Okay, catch you later. Thanks, everyone.
Take care, everybody.
Thank you.